In today's video, we're going to be talking about momentum equations. After watching this video, you should be able to use and apply the momentum equation to basically solve problems. So we're just going to be going through a lot of examples on different types of problems you might see, and then ways that I solve them. Now, my way always isn't the perfect way. If you find other ways that you want to do it, there certainly are more ways than one to solve some of these problems. So let's get right to it. Just a quick review from the previous lesson. Remember, the total momentum of a system is conserved for collisions between two objects in an isolated system. So remember, an isolated system is basically where the frictional force isn't so large that it really causes a huge change, or there isn't some unknown force that kind of comes in and causes a change to the system. It's just basically you're looking at two objects interacting with each other. And momentum being conserved basically means that the momentum lost by one object is equal to the momentum gained by another. And so knowing that, keeping that in mind, that allows us to basically solve problems and be able to figure out the masses and velocities, particularly the velocities of objects after a collision occurs. Okay, so keep that in mind as we start to go through some of these problems. So here's our first example I'd like to talk about. Basically, it says that a 3,000 kilogram truck moving with a velocity of 10 meters per second hits a 1,000 kilogram parked car. The impact causes the 1,000 kilogram car to be set in motion at a speed of 15 meters per second. Assuming that the momentum is conserved during the collision, determine the velocity of the truck immediately after the collision. All right, so first, I like to just draw a quick picture here. So here's this truck. Okay, and it's driving this direction, we'll say. And here's this parked car, okay? And basically, they're going to hit one another. We'll do my boom. And this truck is still moving in this direction, but the car now itself, too, is moving. Okay, so in this picture here, it's at rest. Okay, it's resting. It's not doing anything. Now, remember, the equation for momentum is P equals M times V. Also, something to keep in mind is that the total initial momentum is equal to the total final momentum. Okay, and this backwards E is the summation. The total momentum of the system initially is going to equal the total momentum of the final system. Okay, so basically what we have here is this picture here is my initial, and this picture here is my final. And I know some stuff about things, right? It says that initially this 3,000 kilogram truck is moving at a speed of 10 meters per second, and it hits a parked car of 1,000 kilograms, okay? So let's first deal with the initial momentum piece, okay? So basically what I'm gonna do is I'm gonna write the mass of the truck, which I'll just call mass 1, times the velocity of the truck, which I'll just call v1, plus the mass of the car, which I'll call m2, times the velocity of the car, I'll call v2. Okay, this is all my initial stuff. Is going to be equal to the final stuff. Okay, so let's first calculate the initial. So the mass of the truck is 3,000. The velocity of the truck is 10, and I'm leaving units out again just to kind of save on space, plus the mass of the car is 1,000 times the velocity of the car is 0. Okay, so 3,000 times 10 is 30,000, plus anything times 0 is 0. So basically I have 30,000, we'll call it units of momentum. Okay, that is my initial. Okay, so when everything's said and done, when the dust settles, my final momentum must add up to 30,000. Okay, so keep that in mind. All right, let's do the final piece here. We know that both the masses haven't changed, right? This is still a 3,000 kilogram truck. This is still a 1,000 kilogram car. Let's see, what can we find out? Well, it says that the impact causes the 1,000 kilogram car to be set into motion at a speed of 15 meters per second. Okay, great. So let's do a little bit of calculations. The momentum gained by the little car, actually, let me just write out the equation. M1 V1 plus M2 V2. okay, has got to be equal to 30,000. Okay, it just has to be, right? So the mass of car 2 is 1,000 kilograms times the velocity of car 2, or of the car now is 15, plus a mass of the truck is 3,000, and the velocity we don't know. That's what we want to try to figure out here. Okay, and we have 30,000 over here. All right, so basically if you do this algebra, 1,000 times 15, that'll give you some number, and you subtract from 30,000 and then divide by 3,000, you should get a velocity on the truck of 5 meters per second. Okay, so the truck now is traveling at 5 meters per second compared to 10 meters per second. Basically, its velocity was cut in half by hitting this parked car. Okay, but they both are still moving to the right. And remember, momentum is a vector, and so I did a poor job of showing signs here, but this would be like a plus 5 meters per second, and this car here would be plus 15 meters per second, because I'm just going to assume going to the right is positive, so I made everything moving to the right. Okay, so that's one type of problem you could certainly see like on the homework or on tests or that type of deal. Again, kind of just looking at equations, and I always am about using equations as basically a guide for our thinking. If you have a twofold increase in mass, that results in a twofold decrease in velocity. So mass and velocity, they're inverses of one another. If you have a threefold increase in mass, that results in a threefold decrease in velocity. So you can kind of think about things without even putting numbers in terms of what's going to happen to the velocity of a situation if the mass increases or decreases. Okay, and I think it kind of makes sense. If something becomes more massive, the velocity is probably going to go down. Okay, if something becomes less massive, the velocity will probably go up. And that's basically all this is saying. So let's take a look at an example where we kind of can use that equation idea as a guide for our thinking. Basically, it says a large fish is in motion at 2 meters per second and it encounters a smaller fish that is at rest. The large fish swallows the smaller fish and continues in motion at a reduced speed. If the large fish has 3 times the mass of the smaller fish, then what is the speed of the large fish and the smaller fish after the collision? Okay, well, remember, I'm going to basically say everything to the right is positive. Okay, that's always how I'm going to probably do things. That the total initial momentum must equal the total final momentum. Okay, it just has to be the case. Okay, and basically I'm just going to start setting up our equation here, where basically we have m1 times v1 plus m2 times v2 equals m1 times v1 plus m2 times v2. That's supposed to be an m. Okay. Now, notice in this problem, they don't give us much information. Like, we don't know the actual mass of either fish. But they do give us this, that the fish that swallows the other fish is 3 times more massive. So I'm just going to put a 3 in front of this m. So I'm going to have 3m times the speed of this fish, which is 2, plus the mass of this fish is just 1. So it's just m. I'm just going to have m here, because it's a third as heavy or massive, I guess I should say, as the big fish. And the velocity of this fish, it says it's at rest, so it's times 0. Okay, so that actually doesn't just get canceled out. So if you kind of do this, and we'll just keep mass as m, and we just kind of, in a way, ignore it in a sense, we're just going to have 6m here on this left-hand side. And that is equal to, if we have our m1, which is 3m, plus, times v, we'll call it final, okay, plus the mass of the other fish, which is just m, and then the v final. We can now, again, algebraically say that we're going to pull v final out. And so we have 3m plus m times v final. Okay, so I just basically took v final out of each of these terms and pulled it out to the side like this. The reason why I do that is because then this allows me to basically solve this problem. It's really a key component here. If I throw this up here, basically I have 6m equals 4m times v final. Okay, I just added those two terms together to make it 4m, because now the fish is 4 masses. Okay, and so if I take 6 divided by 4, I would get a velocity of 1.5 meters per second. Okay, and so basically because that larger fish swallowed a smaller fish, it's going a little bit slower, not a lot, but a little bit slower than it initially was because now it's carrying an extra fish in its stomach. All right, let's do another example. Example 3, maybe a little bit trickier, I don't know. It basically says that a 62.1 kilogram male ice skater is facing a 42.8 kilogram female ice skater. They are at rest on the ice. They push off of each other in opposite directions. The female skater moves backwards at the speed of 3.11 meters per second. Determine the post-impulse speed of the male skater. Okay, so this time the signs are going to be important because we have things going in opposite directions. So we need to keep track of our signs because remember, momentum is a vector quantity. Another thing to keep in mind is that the total initial momentum equals the total, I can't write a P if I tried, the total final momentum. All right, so let's figure out what is the initial momentum of the system. I'm not even going to write any numbers down right now because I noticed that this ice skater and this ice skater, the 62.1 kilogram male and the 42.8 kilogram female, are at rest. Okay, so if they are at rest, their velocity is 0. Anything times 0 means they have no momentum. So the initial momentum of the system must be 0. And that's a huge key because that lets us set the right side equal to 0. Okay, and I'll explain what I mean by that in just a second as I work through this. Okay, let's figure out the velocity of this male skater. Okay, so the two of them, and maybe I should draw a picture here. The two of them push off on each other, and this one goes this way and that one goes that way. Okay, we know that, I'll call this one the female. We know that the female ice skater moves away with a speed of 3.11 meters per second. So I'm going to take 42.8 kilograms times 3.11. Okay, that's just m times v, mass times velocity of the female. Now the male skater is going to be its mass, which is 62.1, times the velocity, which we don't know. We're trying to figure that out, right? This whole equation here, this thing that I set up, m1 times v1 plus m2 times v2, must be equal to what? Well, the answer is 0. Okay, and why must it be equal to 0? Because I know the initial momentum was 0, and so the final momentum must be 0. And this is a beautiful thing because it really helps us figure this baby out. Okay, let's see here. What can we do here? 42.8 times 3.11, that equals 133.1. And I'm going to bring that over here to the left. Okay, and so basically what I'm left with is 62.1 times v equals negative 133.1 because I move that over to the left. And now if I do this algebra, 133.1 divided by 62.1, I get a velocity of, and I'm going to put it over here in the left corner, a velocity of negative 2.14 meters per second. Velocity of negative 2.14 meters per second. Now, what does that negative actually mean? The negative just simply means that this ice skater here, this dude here, is moving to the left, okay, in the opposite direction of the female. And that's why the sign piece is kind of important. It is telling you a direction. It's telling you where this skater is going. So hopefully some of those examples give you an idea of what I might be expecting with momentum. That takes care of this video. I'll see you guys next time.